Hi, this lesson is about the complex zeros of a polynomial and the fundamental theorem of calculus. So before we discuss that, we need to review what complex numbers are. The complex number system is the set of all real numbers and the imaginary numbers. A complex number in standard form is a plus or minus bi, where a is the real number part and bi is the imaginary part. So it is possible for the b to be zero, so you wouldn't have an imaginary part. So if you just have a real number, that would be a part of the complex number system. It's also possible for a to be zero, so you would just have bi, an imaginary number, but that's still part of the complex number system. We can add imaginary numbers, subtract them, multiply them, and divide them. So we'll practice all of those skills in these next few examples. In example one, we need to add two complex numbers. Adding two complex numbers, you apply the same rules as combining like terms. So you're going to add the 3 and the 7, which gives you 10, and the 5i plus the negative 2i, which gives you a result of 3i. So your result is another complex number. In number two, I'm subtracting two complex numbers, and because the second one is in parentheses, I need to distribute that negative. So that's what I did on the next line. So I get 1 minus 2i minus 8 minus 3i, and then I'm going to do the same thing I did in number one, is combine like terms. So 1 minus 8 gives me negative 7, and negative 2i minus 3i gives me minus 5i as the imaginary part. In number three, we're multiplying. So when you're multiplying two terms times another two terms, we use something called the FOIL method. FOIL stands for first, outer, inner, and last. So first is 5 times 2, that's 10. Outer are the two that are furthest apart, so that's 5 times 7i, so that's 35i on the next line. The inner are the two that are closest to each other, so that's I times 2, so that's plus 2i. And the last term are the product of the two that are at the end of each complex number, so that gives me 7i squared. So I need to use a definition that was written here above, and that is that by definition, I is equal to the square root of negative 1. And if you square both sides of this, you get that I squared is negative 1. So I'm going to use that to replace the I squared with negative 1. So I just isn't a variable. It represents an imaginary number. And when you square I, you get that I squared is negative 1. So we always replace I squared with negative 1. Once I do that, I have more like terms to combine. So 35i and 2i gives me 37i on the next line. And then this constant of 10, and this one becomes negative 7. When you combine those, you get 3 as your real number plus 37i, the imaginary number. Okay, in the next example, I have a division problem. So I have 7 over 2i, and we need to simplify this. So with imaginary numbers, you cannot have an I in the denominator of an expression like this where you're dividing. And so I need to get rid of the I on the top. And the way you do that, the technique will be to just multiply the top and the bottom by I. Remember, that's equivalent to just multiplying by 1. So we're not changing the value of the original problem. It's just going to look different so that we could get rid of the I in the denominator. So when you do that multiplication on the numerator and the denominator, you get 7i over 2i squared. But remember, I squared is negative 1, so I made that replacement. And so my final answer is negative 7i over 2. It is okay to have an I in the numerator, just not in the denominator. In the next example, we have a similar problem because I have an I in the denominator, but it is different than number 4 because here this is a complex number with a real part minus an imaginary part. So when you have a complex number with a real part and an imaginary part, you need to multiply the numerator and the denominator by the conjugate of that expression. The conjugate just means that you change the operation in the middle. So instead of 2 minus I, you're going to multiply the numerator and the denominator by 2 plus I. So on the top, in the numerator, you distribute. So I get 6 plus 3I. And in the denominator, when you FOIL two conjugates, these right here, 2 minus I and 2 plus I, your outer and inner are going to cancel. So here's first, here's outer, here's my inner result, and then here's my last result. Notice that the outer and the inner will cancel each other out. So when you multiply conjugates, you really just get first minus last, which is what you see here, 4 minus I squared. But there's that I squared again. And I squared is equal to -1. So I made that replacement. So that leaves me with a 5 in the denominator. This is a perfectly good answer, but usually you're asked to present answers in standard form. And standard form just means that you want the real number separate from the imaginary number. So I'm going to separate these, and your final answer is 6/5 plus 3/5 I. Okay, so the I either needs to be next to the fraction, or you could have written it like this with the I in the numerator. So these two are equivalent. Okay, so in the next few examples, we're going to be simplifying some radicals where your result is an imaginary number. So in example number 1, you're asked to simplify the square root of -25. So before you learned imaginary numbers, you would say, oh, this does not have a real number result. There is no real number where you could get an answer for the square root of -25. And that's because the answer is imaginary. So what I did was I used that definition of I squared equal to -1, and I rewrote -25 as 25 times I squared. But both the 25 and the I squared are perfect squares, so when you take the square root of each one, my answer is 5I. This step right here, if you understand it, you don't really have to write it out. If it helps to write it out, you can certainly do that. But in these following examples, I didn't write that second step. The square root of -49 is 7I. In number 3, I have to multiply 5 times the square root of -36. So the square root of -36 is 6I, and when you multiply it by 5, you'll get 30I as a result. And in number 4, you have to take the square root of -144, which is 12I, but then when you multiply it by a third, 3 and 12 are both divisible by 3. So the 3 becomes a 1, the 12 becomes a 4. So your final answer is 4I. All right, so now we're going to solve some polynomials where our result is a complex number. So it is possible to get complex numbers where you have an imaginary part as your solution, or you might just get real numbers, or you could have a combination of both. So these two examples that I'm showing you here are two second-degree polynomials. And so at most, you're going to get two zeros or roots, or possibly x-intercepts. If you get an imaginary result, they are not x-intercepts. You can't graph them, but they are still considered zeros or roots. So in order to solve the first one, x squared plus 4, you can't factor this. So you have the choice of either using the quadratic formula or using the square root method. Square root method is faster. So what I did was I subtracted 4 from both sides. I get x squared equals -4. And then I took the square root of both sides of the equation. And when you do, you get that x is equal to plus or minus 2I. So I get two imaginary number zeros or solutions to this equation. They are not x-intercepts. And in fact, this quadratic function doesn't cross the x-axis at all. So this is no x-intercepts. So this graph actually, just to show you what it would look like, has a vertex at 0, 4, and the graph would go like this. So you can see in the picture, it's never going to touch the x-axis. 4x squared plus 9 has similar results. Again, you can't factor it, so you can solve it with the quadratic formula, or you can use the square root method, which again is faster. So I'm going to subtract 9 from both sides and then divide both sides by 4 and then take the square root of both sides. And when you take the square root, when you use that method, you have to make sure to put a plus or minus in front of the answer. So my answer here becomes plus or minus 3/2 I. Again, these are two imaginary number solutions. This one also has no x-intercepts. And the parabola would look similar to the one that I drew here on the left. Okay, well now we're going to look at some higher order polynomials. So an nth degree polynomial has at most n real number zeros. So if you have an nth degree polynomial, you are going to get n real number zeros or less. That's what at most means. You're not going to get more than n real number zeros. So in this case, this was a second degree polynomial. I had 0 real number zeros. There were none because they were both imaginary. So at most means that I would have gotten 2 or less real number zeros. In the complex number system, an nth degree polynomial will have exactly n zeros. That includes the multiplicities. So when you look at all complex numbers, including real and imaginary, you're going to get the same number of zeros as the degree. So this one definitely shows that. It's a second degree polynomial. I got 2 complex number zeros. This is a second degree polynomial. I got 2 complex number zeros. So remember, a real number is a complex number, but an imaginary number is a complex number. It's not real. So in this polynomial here in brown, I have p of x is equal to x squared plus 1 times x minus 2. If I were to multiply this out, this would be a third degree polynomial. So I expect to get 3 zeros. They may be real, they may be complex, or I might have a combination of both, but no more than 3. So when I set it, the first factor equal to 0, I again am using the square root method, subtract 1 from both sides, take the square root, x is equal to plus or minus I. Those are two imaginary number solutions. This is part of the complex number system. When I take the second factor and set it equal to 0, I get 2. That is one real number solution. So in total, I have 3 zeros. 2 imaginary, 1 real, to match with the third degree polynomial. Okay, so if a 0 is a complex number, and again, it's of the form a plus or minus bi, then so is its conjugate. So what's a conjugate? If a minus bi is a 0, then a plus bi will be a 0 of the function, and vice versa. So that's why here, both positive I and negative I were solutions or zeros of this polynomial. You can't have one without the other when you're looking at the complex number system. Here, those are conjugates, and these two are also conjugates. So that will be consistently true for any polynomial. If you have a complex number or an imaginary number as part of your solution, so will its conjugate pair. They come in pairs. That is not the case for real numbers. Like here, 2 is a solution, but negative 2 is not. Okay, so it's only true for the complex numbers with an imaginary part. All right, so now we'll talk about the fundamental theorem of calculus. So it says uh, every polynomial of the form p of x equal to a sub n x to the n plus a sub n minus 1 x to the n minus 1, etc., all the way to a sub 1 x to the first plus a sub 0, as long as your n is greater than or equal to 1, which means it has to be linear, a linear function or higher, like quadratic, third degree, fourth degree, etc., and the leading coefficient is not 0. With complex coefficients, so all of your coefficients have to be part of the complex number system, meaning they can be real or imaginary, then you will have at least one complex 0. And remember, complex doesn't mean that it has to have an imaginary number. Complex numbers is equal to the set of real numbers and imaginary. Okay. So, in other words, you'll be able to solve any one of these. It could be a real number result, but it could be imaginary or a combination of both. So this is what I was just emphasizing here. It applies if all of the zeros are real numbers, since real numbers are also part of the complex number system. Okay, so we have something called the complete factorization theorem. So if p of x is a polynomial of degree n greater than or equal to 1, then there exists complex numbers a, where a is the coefficient of this product here, c sub 1, c sub 2, c sub n, with a not equal to 0. Again, if this was 0, the whole thing would just be 0. Such that p of x is equal to a times x minus c sub 1, x minus c sub 2, x minus c sub n. What that means is um, if these are like zeros of your polynomial, then you can write each one as a factor where you put the opposite sign of whatever this number is. So if 2 is a 0 of a polynomial, then x minus 2 is a factor of the polynomial. So you can always rewrite it as a product of factors. All right, so we're going to use some of this information. So we have p of x is equal to x to the third 4x squared plus x plus 4. This is a third degree polynomial, and you're asked to find all the zeros of p of x. Okay, so p of x is actually something that can be factored by grouping. So that's what I did here. I factored out an x squared from these two, and then I factored out a 1 from these two. So on the next line, I get x squared times x plus 4, and then I get 1 times x plus 4. The common factor for these two products is x plus 4, so I wrote that, times what was left, and that's the x squared and the 1. So x squared plus 1. And that whole thing is set equal to 0, and then I'm going to solve this similarly to the way I solved one earlier in this lesson. I'm going to take each factor and set it equal to 0. So this one becomes x squared equals negative 1. And if you take the square root of both sides, you'll get x is equal to plus or minus I. And on the right side, you're going to get x is equal to negative 4. Negative 4 is a real number, and plus or minus I is two conjugate pairs of imaginary numbers. So in total, I have 3 zeros, and that's what we expect because it is a third degree polynomial. Part B of this problem is asking you to state the polynomial in terms of its complete factorization. And that was the theorem that I gave you a minute or two ago, which is to write your polynomial as a product of linear factors. So the x equal to negative I, and 4, this is the factor associated with negative I, this is the factor associated with positive I, and this is the factor associated with 4. So P of x equals x plus I, x minus I, and x minus 4. And if you were to expand that out, multiply it out, it would equal the original polynomial. All right, so here, the one in blue, we have P of x is equal to x to the third minus 2x plus 4. And the directions are the same as the last one, but we have to take a different approach. We have to find all zeros of P of x. And again, we should find 3. And then we're going to state the complete factorization, which means we want to write it as a product of factors. So the reason why we have to take a different approach is because P of x is not factorable. So we have to try to find another way to figure out how to break this down so that we can identify the zeros. So I'm going back to a previous lesson, which was the rational root theorem, which means that you can list all of your potential rational roots, which would be real numbers. And that's going to be all the factors of 4 divided by all the factors of the leading coefficient, which is 1. And those potential zeros are plus or minus 1, plus or minus 2, or plus or minus 4. And then if you recall that earlier lesson, the way you would figure out which factor works is that you would use synthetic division to divide these numbers into the original polynomial, and the one that gives you a remainder of 0 would be a factor. And so in this case, I didn't show all the work, but negative 2 would work, and the work is right here. So you list the leading coefficients, and here an x squared term is missing, so that's why I have a 0 there. I have x to the third minus 2x plus 4, so there is no x squared. So when you put your polynomial inside of the division bar here, you have to put a 0 to hold the place for the x squared term. So when you do the synthetic division, you end up with a remainder of 0, which means that the factor x plus 2, again, you pick the opposite sign, is a factor of this polynomial. And then these numbers get rewritten as this quadratic x squared minus 2x plus 2. Okay, so that doesn't give me all of my answers. I've only found one so far, and I should be able to find 3 zeros. But I do have a quadratic expression here, a quadratic equation, and it's not factorable, so I'm going to use the quadratic equation to solve it. And the quadratic equation is right here. You have to pick out your a, b, and c from this, which is a is 1, b is negative 2, and c is 2, and plug in those numbers right in here. And when you work that out, you get 2 plus or minus square root of 4 minus 8 over 2, which works out to be 2 plus or minus the square root of negative 4 over, negative 4, which becomes 2y all over 2. And when you divide them both by 2, you get, again, your conjugate pair of complex numbers, 1 plus or minus 2y. So the 3 zeros are negative 2, which is the one we found earlier, 1 plus I, and then 1 minus I. So I have one real number result and two complex numbers. So once you figure out what the zeros are, then you can state what the complete factorization is. So you want to write each of these zeros in terms of its corresponding factor. So the one associated with -2 is the factor x plus 2. The one associated with 1 plus I is x minus 1 plus I, but on the next line I distributed that minus. And the one associated with 1 minus I is x minus 1 minus I. So again, I just distributed that minus on the next line. So the complete factorization of the original polynomial is what you see inside of that box. And again, expanding that, if you were to multiply it out, it should equal what the original polynomial was. Okay, so multiplicity plays a role here. And again, we talked about multiplicities in a previous lesson. So recall that the multiplicities of a zero impacts the shape of a polynomial when the zero is a real number. As long as it's a real number, then whether that factor comes up an odd number of times or an even number of times impacts what the shape of the graph is and what it looks like. So since an nth degree polynomial has exactly n zeros, you have to count the multiplicities in that number, whatever n is. So if something has a multiplicity of 2, that would count as 2 of the zeros out of whatever the number n is. So the zeros theorem states that for every polynomial of degree n greater than or equal to 1 has exactly n zeros, provided that a zero of multiplicity k is counted k times. So that's basically just a repetition of what I said here above in green. So here's a polynomial that's already completely broken down. I have x minus 2 times x plus 2 to the third, x plus 5 to the second. So if I were to expand this out, the way you figure out what the degree is, in the first one, this is my x's to the first power. If I were to expand this out, my x here would be to the third power. That would be the highest degree. And if I were to expand the last one out, my highest x would be to the second. So if they would all get multiplied together, remember you add exponents when you multiply. So 1 plus 3 plus 2 means that this would be a 6-degree polynomial. So that means I should be able to count exactly 6 zeros, including the multiplicities. So x minus 2 has a solution of 2 with a multiplicity of 1. X plus 2 to the third power has a solution of -2 with a multiplicity of 3. And x plus 5 has a solution of -5 with a multiplicity of 2. So if I add up all the multiplicities, 1 plus 3 plus 2, that equals 6, which is the same number we expected from because it's a 6-degree polynomial. Okay, so that's what we mean by counting all of the multiplicities. This isn't just one solution, although it is a repetition. That solution would come up 3 times, so that means -2 would be counted 3 times. All right, so in the next example, we're going to find some of these solutions, and there will be some multiplicity here. So we want to find all zeros and the complete factorization of f of x equal to x to the fourth plus 18x squared plus 81. This is a 4th-degree polynomial, which means I expect to find 4 zeros. So this one actually is factorable. This factors into x squared plus 9 times x squared plus 9. So these two factors are the same. So you really only have to solve one of them. So if I solve one of them, I use again the square root method. I get x squared equals -9. So x is equal to plus or minus 3i. So if I were to solve this one, I would get the same result. That means that I have 2 unique zeros, -3i and +3i, but because this factor would have given me the same answer. Each one has a multiplicity of 2. So the total number of zeros when you count the multiplicities is 4, the same number as the degree. Okay. The graph of this polynomial is here, just to emphasize this a little more. If you were to plot this, I used a graphing calculator app. This is the number 081, and then the graph increases on both sides. There's nothing below it, so I didn't show the bottom half of this graph, because there's basically nothing there associated with this function. So you can see that it will never cross the x-axis, which is why all of my zeros were imaginary numbers. So when you write these in terms of their factors, their complete factorization, it's x plus 3i and x plus 3i twice, so it's to the second power, and x minus 3i times x minus 3i, which is x minus 3i to the second. And again, if you were to actually multiply this out, it would equal the original function. Okay, so we're going to go on. We can find the polynomial function if you're given the zero. So in other words, go backwards. We've been solving for the zeros, but if you are told what the zeros are and you're asked, well, what's the polynomial associated with it, you can do that by just writing out your complete factorization and multiplying them out. So we want to find the polynomial q of x with a degree of 3, with the zeros 3, positive 2i, and negative 2i. So each factor associated with those 3 zeros are x minus 3, x minus 2i, and x plus 2i. You have to multiply those 3 binomial expressions together. So I did 2 at a time. So I decided to multiply these 2 first. And again, by the FOIL method, that's the expression in the second parentheses. So that's x squared plus 2i minus 2i minus 4i squared. The 2 i's will cancel out. And when you replace the I squared with negative 1, you're left with multiplying x minus 3 times x squared plus 4. And then I applied the FOIL method again. So first term is x to the third, outer is 4x, inner is negative or minus 3x squared, and last is minus 12. That's a perfectly good answer, but typically we write our polynomials with the highest degree first and then decrease from there in order. So I just rearranged the second and the third term. So q of x, which is what you were asked to find, is x to the third minus 3x squared plus 4x minus 12. Okay, here's another one. We want to find the polynomial p of x with a degree of 2 with zeros 2 plus I and 2 minus I. So again, these are my 2 conjugate pairs. I only expect 2 because it's a second degree polynomial that I should come up with. So the factor associated with 2 plus I is x minus 2 plus I. Factor associated with 2 minus I is x minus 2 minus I. So first I just distributed this negative, and I get this result right here. So I'm left with 3 terms times 3 terms. So you can't do FOIL method when you have 3 terms times 3 terms. So it's just going to take a little longer, but just need to be careful not to miss anything. So first you distribute the x across all of that. And when I do, I get x squared minus 2x minus ix. Then I have to distribute the middle term, the negative 2, across those 3. So I get minus 2x plus 4 minus 2i. And then I have to distribute the minus I across those 3. And that gives me minus ix plus 2i minus I squared. So several things cancel and they are slashed in blue. So they no longer appear on the next line. And I also replace the I squared with -1, so it becomes minus -1, which is 1 on the next line. And then the last step is just to combine the constants 4 and 1. So the polynomial with those two zeros is x squared minus 4x plus 5. And if you were to solve this with the quadratic formula, you would get this answer. Okay, so here's another one. We want to find r of x of degree 4 with zeros 1 minus 2i and 1 where 1 has a multiplicity of 2. Okay, so I should have 4 in total. So here's 1, and this one has a multiplicity of 2, so I only have 3, but you need to have 4 in total. But remember, I stated this earlier, your complex numbers come in conjugate pairs. So if 1 minus 2i is a 0, then so is 1 plus 2i. So even though it's not stated in the original problem, you need to realize that just based on a theorem that I mentioned earlier. So all of those zeros, all the ones that I know, now have to get organized in its complete factorization. And so the first one, 1 minus 2i, becomes x minus 1 plus 2i. The second complex number becomes x minus 1 minus 2i. And the 1 with a multiplicity of 2 is written as x minus 1 to the second power. So just like previous examples, I need to now expand that out, multiply out these factors. So the x minus 1 to the second just becomes x squared minus 2x plus 1. That was done by FOIL method. But to get all of this, I have to do the same thing that I did in the last example, which is distribute the x. So this x gets distributed, then the -1, and then the 2i. And so that's when you get everything that's inside of the first parentheses. But inside of that first parentheses, again, there were several like terms that canceled each other out, and they are slashed in blue. So when I put it all together and replace the I squared with -1, the first polynomial is x squared minus 2x plus 5, and that now has to get multiplied by the second one, which is x squared minus 2x plus 1. And then we have to repeat that process all over again. We're going to have to distribute the x squared across this. So I get x to the 4th minus 2x to the 3rd plus x squared. So that's the first set. When I distribute the minus 2x, I'll get minus 2x to the 3rd plus 4x minus 2x. And when I distribute the 5, I'll get plus 5x squared minus 10x plus 5. There are several like terms in this second to last line. So when you combine the like terms, you get x to the 4th minus 4x to the 3rd plus 10x to the second minus 12x plus 5. And so that's what we were asked to do, to find what r of x is. And so here it is. Okay, so here's one for you to try. Find the 4th degree polynomial s of x with zeros 2i and 3i. So remember, you should have 4 zeros in total, but these imaginary numbers come in conjugate pairs. So if 2i is a 0, so is negative 2i. If 3i is a 0, so is negative 3i. Then you have to write the factors associated with all 4 of those zeros and then multiply it out. So give it a try. Good luck.